The first few times you hear the term stress tensor, it tends to create a sense of confusion or foreboding. Why do we need something as complex as a tensor? In the case of stress, it is not really terribly complex, and I want to give you a short overview of where the stress tensor comes from. And this is not going to be a complete derivation, but enough to give you a sense of the general function of the thing. We could ask a simple question about forces and stresses. For example, if I had a surface, I could apply a force. Everybody knows what that means. It has a magnitude and it has a direction, and we can apply it to a particular location. It's also fairly simple to think about the forces acting on a body which is underground, or a small element within a body. So imagine this little dA or dV if we were thinking in 3 dimensions, and it's got forces acting on it in all different directions. Now that's easy enough to think about too, and the simplest way to visualize that is the simple case of hydrostatic pressure. And that is the situation where the pressure is the same in all directions, just as would occur underwater, where if we have an unusually shaped object, the pressure or the force per unit area that's acting on it is everywhere perpendicular to the surface and equal in magnitude at the same depth. If this is a force which is created by the weight of water of some depth z above our heads. So here the pressure of the water would be equal to the density of water times the acceleration of gravity times the depth below the water, and it would apply in all different directions equally. A more complex but very equivalent situation is that of the stress underground, where we may be at some depth z below the surface, and now we're in a solid material rather than a fluid, and so the stresses acting on the body may be harder to describe, but they're still there. And this is the situation that we're going to think about mostly. Before we go any further, a little bit of nomenclature. Let's recall the distinction between stress and force. Stress is a force per unit area. So, for example, if I had a particular force, F, that I was applying over a very small area, that would create a large stress, as opposed to the same force applied over a much larger area, and that would create a smaller stress. It's the bed of nails idea, where if you were lying on one nail, that would be very painful. But if you're lying on 1,000 nails, the weight of your body is spread out over a much larger area, even though each area by itself is a little pinpoint. Or why snowshoes work to keep you from falling down into the snow. Your weight is distributed over the area of the snowshoe rather than the much smaller area of your boot. Also, there are 2 different flavors of stress, if you like. One of them is a normal stress, which operates parallel to the normal of the surface that it's acting on. So there's 2 dimensions here. If the surface is horizontal, so this little nu here is the outer normal, and it's pointing perpendicular to the surface, the normal stress, which we usually use sigma to denote, acts parallel to the normal stress. And we give that some nomenclature. Let's give ourselves an x and a y axis. With these coordinate axes, we can specify that this stress sigma is pointing in the y direction, or pointing in a direction parallel to the y-axis, and is also acting on a plane whose perpendicular points in the y-axis. We'll discuss the signs of these things later. But the repeated subscript, a YY, indicates that it's a normal stress acting in the Y direction on a plane whose outer normal points in the Y direction. Compare that to a shear stress in which the plane may have the same orientation. So there's its outer normal, still pointing in the Y direction. But the action of the stress is in the X direction, and we could call this sigma xy to indicate that it acts in the X direction on a plane whose outer normal points in the Y direction. And it's quite common to also describe shear stresses with the variable tau, although we still want to keep the subscripts xy to distinguish this from, for example, a shear stress that points in the Y direction on a plane whose outer normal is parallel to the X direction, or Y and Z, or X and Z, for example. And as I mentioned before, we're going to stick with 2 dimensions here, but these ideas are all perfectly applicable to 3. Now let's take care of the signs of these various terms. We actually have 3 sign conventions that we have to consider. The first is the direction in which forces act in the summation of forces. The second is the compression versus tension convention. And the third is counterclockwise versus clockwise when we're summing moments. And we'll discuss these as they come about. First of all, let's start by looking at some forces that act in the X direction on planes whose outer normal also points in the X direction. And so these are sigma xx, and those are normally considered positive because both of these vectors are positive. The force acts, or the stress acts, in the positive X direction, and the outer normal is also in the positive X direction. On the other side, we have an equal and opposite force acting in the minus X direction, but it acts on a surface whose outer normal also points in the minus X direction. And because of that, those 2 minus signs, we consider that to be a positive value as well. Now let's think about negative stresses. If I have a stress in the Y direction acting on a plane whose outer normal points in the Y direction, in this case up on the top, the force is acting in the minus Y direction, but the outer normal points in the plus Y direction. And so this would be considered a negative sigma YY. But we're going to change that a little bit in just a moment. But this is consistent with the interplay between the sign of the action of the stress and the sign of the outer normal. And similarly down here, this sigma YY is acting in the positive Y direction, but on a plane whose outer normal points in the minus Y direction. And so it is also regarded as negative. Now this is the normal sign convention in mechanics. You would find this in continuum mechanics, for example. But in geotechnical applications, it is typically not the sign convention. In geotechnical engineering and a number of other disciplines, because we are generally working underground, all forces are in compression, and so we'd be writing negative signs everywhere if we adopted this sign convention. So for certain applications, we reverse this sign convention, and we consider compression to be positive and tension to be negative. But again, that's for geotechnical applications. Now let's think about shear stresses. And I have written the signs on the normal stresses acting in the X and Y directions using the geotechnical sign convention here. The shear stresses may look like this. Let's look at the right-hand and left-hand sides first. I'm going to apply a shear stress like this that acts in the plus Y direction on a plane whose perpendicular points in the plus X direction. And a shear stress over here, I'm going to put its sense of action this way so that these 2 stresses on the right-hand side and the left-hand side would impart a counterclockwise motion to the body if it were free to move. And by sign convention, we're going to let those be a positive rotation. And we can call them tau yx and tau yx. And you notice that these are pointing in the positive y direction on a plane whose outer normal points in the positive x direction on the right, and on the left a negative y direction acting on a plane whose perpendicular points in the negative x direction. So by the subscript convention, these would both be considered positive. And now, if we look at the whole thing, we can see that the forces could be in balance in the x and y direction, and also the moments cannot be in balance because we don't have anything opposing this counterclockwise motion that's imparted by tau yx. So let's apply another force, a shear stress, times this area, applied to the top and bottom, which will have this sense. They will act in a clockwise direction. And these I will call tau xy because they act in the top in the plus x direction on a plane who acts in the plus y direction, and on the bottom the shear stress acts in the minus x direction on a plane whose outer normal points in the minus y direction. And I will call those tau xy. And those are all positive. In terms of the subscript notation, however, once again, for summing forces, we have positive x, negative x, positive y, negative y for our sign convention, and we have compression positive and tension negative. And for moments, we have counterclockwise positive and clockwise negative. And you do have to keep in mind when you are balancing things, which of these sign conventions is the relevant one.
But now that we have the nomenclature to discuss different types of stress and different orientations of stress, let's ask in a little bit more detail what it means to ask a question about what is the stress at some depth z in the ground. It's clearly not a perfectly straightforward answer because there is no single force acting. There's some combination where, for example, if I consider a horizontal surface, evidently there is a sigma yy acting on that horizontal surface, or if we look at a vertical surface, there is some sigma xx acting on that surface. So it's different depending upon what orientation we're looking at in the ground. And in particular, what if I asked about some intermediate orientation? Rotated, say, by some angle theta relative to the horizontal. What's the stress acting on that surface? It clearly has something to do with sigma xx, sigma yy, but we don't know exactly what. And I want to add also that we could ask exactly the same questions if the initial state of stress in the ground was perhaps something like this, where I had some shear stresses acting together with some normal stresses. Okay? We could still, if we knew what these values were initially, we could answer the question of what the stresses are on a horizontal surface or a vertical surface, because they would be simply what we have given to us here acting on the vertical and horizontal sides of this box. And don't forget that this little box, or dA in 2 dimensions, is infinitesimal. It is small. We're going to let that shrink to 0
so that it becomes the actual state of stress at a point, even though we do our little drawings and force balance analyses on a box of finite extent, where this is something where we take the limit as the size of that box goes to 0, and the stresses that we calculate become stresses at a point. So it's evident so far that at some point in the ground, we have a state of stress that depends upon what orientation we choose to look at in the ground. Here's another way of thinking about that.
I'm going to blow this up into a larger scale and show our little delta A here sitting at some depth y in the ground. And it is feeling the effect of normal stresses, sigma yy in the vertical and sigma xx in the horizontal. Now, if I were to momentarily remove these stresses here and ask you what forces would have to act on the right-hand and lower sides of this square to restore equilibrium, it would be a simple matter to put these in and say, well, that sigma yy on the top has to be reacted to by the sigma yy on the bottom, and the sigma xx on the left has to be responded to by the equal and opposite sigma xx acting on the right. However, let me ask a slightly different question, which is what happens if we start with a state of stress like this, but then think about making a cut in the material and removing one side of this from the picture. Now, I think you can see that if this is going to have equilibrium restored to it, there needs to be some reaction stress F acting in a sense which is both downward and to the left, since the stresses that it is having to respond to are acting upward and to the right. And we can solve for what the x and y components of this reaction stress would have to be. However, we don't balance stresses, we balance forces. So we have to turn these stress components into forces by applying them times their appropriate areas. And to do that, let's call the length of this cut surface here dl. And I'm calling it dl just to remind us that this is small. We're taking the limit as this box goes to 0. And the reason for that is contained over here. That's because we want the same overburden stress to apply across the entire box. This box is small enough that the top of the box and the bottom don't feel any significant difference arising from the stress, from the overburden, which is acting overhead. And in that case, the vertical side of this would be dl times the cosine of theta, where theta is this angle here. That's the angle of this cut relative to the vertical. And the side of the triangle at the bottom would be dl times sine of theta. Now, let some forces in the horizontal direction, first the x direction, positive to the right, and we have a positive sigma xx acting on a face that is of length since we're in 2 dimensions, dl times the cosine of theta. And acting counter to that, in the negative x direction, we have the stress Fx, and it is multiplied times dl. And those two should be equal to 0. Summing forces in the vertical direction, that is the y direction, and convention positive up, we have sigma yy acting on a surface of length dl times the sine of theta minus the reaction force Fy acting down, and it's acting on a surface dl, and that's also equal to 0. And so we can see that the dl's all cancel, and we have the fairly obvious result that f of x is equal to sigma xx times the cosine of theta and f of y is equal to sigma yy times the sine of theta. Well, now we can see that the relative magnitude of these two stress components is determined both by the angle of the cut and by the magnitude of sigma yy. So let's use that information to find out what the angle of F is relative to the geometry of the triangle. This time I'm going to do the force balance including the shear stresses, just so that we have something a little bit more complete. Now I will draw in as before. I have my sigma xx acting on the left, and I have a sigma yy acting on the bottom. And now I am going to add a shear stress pointing in the positive y direction on the left-hand side here, and I'm going to call it tau yx, and over on the bottom I've got another shear stress, and I'm going to put it in the opposite sense of rotation so that we can zero the moments, and I'm going to call this one tau xy. And those are the applied stresses, or the stresses that we know, and now we have to come up with an expression for the unknown reaction force F, which has components Fx and Fy, and evidently the x component of the reaction force F has to react to sigma xx on the left and tau xy on the bottom, and the component Fy has to react to sigma yy on the bottom and tau yx on the left. Remember that we don't sum stresses, we sum forces, so we have to multiply each of these stresses by their appropriate area. And this time, rather than using dl and cosine theta, I'm going to just call this side here C, that's its length. This side here will have length A, and the bottom will have length B. And then finally, the geometry of the triangle is given by this angle theta. Now we can start balancing forces. And I'm just going to draw in the components Fx and Fy explicitly. We can see those. And let's start by summing forces in the x direction, the horizontal. And those consist of sigma xx over on the left-hand side, and it acts on a surface of length A, and acting with that is the tau xy on the bottom, which is acting on length B, and then countering that is the x component of the unknown force, and it acts on length C. And those have to be equal to 0. And now summing forces in the y direction, positive up, we have tau yx, and that's multiplied by A, plus sigma yy times B minus f of y times C. And those should also equal 0. Now let's simplify these and solve them for the terms Fx and Fy. Looking at the upper of the two equations, Fx is equal to sigma xx times A over C plus tau xy times B over C. And Fy is equal to tau yx times A over C plus sigma yy times B over C. Now, the thing to notice is that the ratio A over C is actually equal to the cosine of the angle theta, and B over C is the sine of theta. I bring this up because we're going to see that the unit vector eta is actually composed of the direction cosines, which will be eta x and eta y, and those are going to be the cosine of theta and the cosine of 90 minus theta. let's look at that a little more closely in a little coordinate system of its own. Here is x and y, and here is a arbitrary unit vector, and it has these components, eta y and eta x. And if this is the angle theta, and this is 90 minus theta, and you can see that the theta in this little drawing here is the same theta as up in the main triangle. As theta goes to 0, that cut surface becomes vertical and the unit vector eta becomes horizontal. And over here, as theta goes to 0, the vector eta also goes to 0. So if this thing is of unit length, we can see that eta x is going to be equal to the cosine of theta, and eta y is going to be equal to the cosine of 90 minus theta. And those are the direction cosines of the unit vector. Now, because of that, we can rewrite our expression in the lower box immediately above in this fashion. We can write this as theta xx times nu x, that's cosine theta, plus tau xy times eta y, and that is all equal to the x component of the reaction stress, and the second line here becomes tau xy times eta x plus sigma yy eta y, and that's equal to f of y. And now we can rewrite this in a matrix formulation that looks like the following. Sigma xx tau xy tau yx sigma yy, all multiplied by the vector eta x, eta y, gives us the reaction force Fx and Fy. That's an important result. What it's showing us is that with the stresses written in this matrix form, I can take any cut surface represented by its unit normal and perform this multiplication, and what I will get from it is the stress vector acting on whatever surface eta represented. And that really tells the story of what the tensor is in this setting. The tensor, and I should emphasize that this thing here is the matrix representation of the tensor in this particular coordinate system. The tensor itself has got many more properties that we're not describing here. This is just what the tensor does functionally when we're thinking about stresses. It is a matrix of numbers which, when we multiply times a particular orientation represented by a normal, we get back from it the forces that would act on that cut surface. And this goes back to the business of what is the state of stress in the ground. And to answer that question, you have to go a little bit further and specify what direction in the ground we're looking. Are we looking at a horizontal orientation? Are we looking at a vertical orientation? Or are we looking at something in between? So evidently, when we ask the question, what's the stress in the ground, we're asking a slightly different type of question than we might ask about other physical properties. And let me compare the stress tensor, which is actually formally a second-order tensor, and compare it to a first-order and a zero-order tensor. Let's start with the zero-order tensor. A zero-order tensor is simply a scalar. An example might be temperature. We can describe temperature with one number. It may be a function of space and time, but it can be described with simply a single number with some units. And now a first-order tensor is what we normally think of as a vector. And let's use velocity as an example. If I ask, what's the velocity of a projectile, v, it's also a function of space and time, generally, but it contains both a direction and a magnitude. So here, like with the temperature, with the zero-order tensor, we go to a particular place and a particular time, but to answer the question of what is the velocity, we have to give a more complex answer than a single number. In fact, we have to give 3 values in 3-dimensional space to specify both the magnitude of the velocity and which way it's going. And now we can see that the second-order tensor of stress, and I should add that other examples of the second-order tensor could be electrical conductivity, thermal conductivity. There's many other properties that are described by a second-order tensor, which at this point we start calling them tensors. And in this case, we have to go to a certain place, maybe a certain time, but once we get there, we have to specify not only where we are, but what direction we're looking in. So let's add an extra variable here, the look direction. And that is because in the case of the stress, we can go to a certain place and a certain time, but once we get there, we also have to specify a certain orientation, a certain look direction at that location before we can answer the question. And so we have the matrix that represents the tensor in a particular coordinate system. We multiply that times the direction that we're interested in, and from it we get the reaction stress, or the stress produced by the external or far field forces that apply to that particular orientation.